Have you ever stopped to wonder what consciousness really is? Or why the smallest particles in our universe, like electrons and photons, behave so strangely, defying the rules of everyday life? Some scientists think these two mysteries might be connected. The theory of quantum consciousness suggests that our minds could operate on the same mind-bending principles that govern particles at the quantum level. In quantum mechanics, particles can exist in multiple places at once, and observing them changes their behavior. Could our minds work in a similar way, with thoughts and ideas existing in multiple states until we focus on them? And could consciousness itself be a sort of observer, affecting reality on a quantum scale? This idea challenges what we know about both physics and self-awareness. As we explore, we'll see how quantum mechanics and consciousness might actually be linked in ways we never imagined. In our everyday experience, just looking at an object, like a cup on a table, doesn't make the cup act differently. But in the quantum world, things don't work the way we expect. Here, the simple act of observing a particle can change how it behaves. This puzzling idea is known as the observer effect. What exactly is the observer effect? It's a phenomenon where the state of a quantum system is altered by the act of measurement. Think about it. Why should observing or measuring something cause it to change? To understand this better, let's start with some examples from quantum physics. When scientists measure the position of an electron, the electron's behavior changes. If they measure its momentum, that changes too. So what's going on? Why does it seem like quantum particles react to being watched? One explanation is that measuring a quantum particle isn't as simple as taking a quick look. In quantum mechanics, measuring means interacting with the particle in some way. For instance, to detect an electron, scientists might shine light on it. But light, even in tiny amounts like a single photon, carries energy. When that energy hits the electron, it changes the electron's state. It's like trying to watch a leaf floating on a pond by dropping a pebble into the water. The pebble disturbs the water and moves the leaf, so the simple act of observing affects what you're trying to see. But is it just about interaction? Or is there something deeper, something more connected to the nature of quantum reality itself? This question brings us to a concept known as the collapse of the wave function. In the quantum world, particles are described by a wave function which gives the probabilities of where they might be or how they might behave. Before you measure a particle, it exists in a superposition of states, meaning it's in multiple states at once, like being in several places simultaneously. When you observe or measure the particle, the wave function collapses, and the particle settles into one definite state. Why does this happen? No one fully understands. Some physicists suggest that the act of measurement forces nature to make a choice, selecting one outcome from all the possibilities. Imagine having a deck of cards where each card is both red and black at the same time. When you pull out a card and look at it, it becomes either red or black. The act of looking makes the card choose. This is a strange way to think about reality, but it's what the mathematics of quantum mechanics implies. The idea of wave function collapse is also linked to one of the most famous thought experiments in physics, Schrödinger's cat. Here's how it goes. Imagine a cat inside a sealed box. Inside the box, there is a radioactive atom with a 50% chance of decaying within an hour and a 50% chance of not decaying. If the atom decays, it triggers a mechanism that releases poison, killing the cat. If the atom doesn't decay, the cat remains alive. Since the atom's decay is a quantum process, it exists in a superposition of decayed and not decayed states. And because the cat's life depends on the atom, the cat is also in a superposition, both alive and dead at the same time. Only when you open the box and observe the cat does it collapse into either being alive or dead. This thought experiment raises a simple yet mind-bending question. Is the cat really both alive and dead until someone looks? Or is there some hidden process we don't understand yet? Schrödinger used this example to illustrate how absurd quantum superposition sounds when applied to everyday objects. But it's also a way to highlight the impact of observation on quantum systems. Does this mean that consciousness itself plays a role in determining reality? That's another mystery. Some physicists have speculated that consciousness is key to the collapse of the wave function. They argue that the act of a conscious observer measuring a quantum system causes the collapse. In this view, the universe only becomes definite when it's observed, but not everyone agrees. Many scientists believe that simple interactions with measuring devices, not consciousness, are enough to cause the collapse. For them, it's about physical processes, not human awareness. Why does this matter? Because it gets to the heart of what quantum mechanics says about reality. If consciousness plays a role in quantum measurement, it could mean that our minds have a deeper connection to the universe than we realize. But if consciousness isn't involved, it still leaves us with the puzzle of why reality behaves this way. One interpretation of quantum mechanics that tries to address these questions is called the Copenhagen interpretation. According to this view, quantum systems don't have definite properties until they are measured. An electron, for instance, doesn't have a specific position or momentum until you measure it. Instead, it exists as a range of probabilities described by the wave function. Only when measured does it settle into a definite state. The Copenhagen interpretation emphasizes the role of measurement in shaping reality, but it doesn't explain why this happens. Other interpretations take different approaches. Some suggest that quantum particles are always in definite states, but we just don't have the full picture. Still, the debate continues, and no single explanation has been universally accepted. If you think about it, quantum mechanics is like a giant puzzle with missing pieces. We have rules that work incredibly well for predicting outcomes, but the deeper why remains elusive. Is the universe fundamentally built on probabilities? Does the act of observing really shape reality? These are questions that keep physicists up at night. Another thought-provoking question: what role, if any, does consciousness play in the universe? If observing a particle changes its behavior, does that mean we are active participants in shaping reality? Or is observation just a byproduct of how quantum systems interact with each other? The observer effect doesn't just exist in theoretical physics. It has real-world implications. Quantum measurements are the basis of technologies like quantum computing and secure communication methods. The more we understand about quantum measurement, the more we can harness these principles for practical use. But even with all our technological advances, the basic mystery remains: why does observing a quantum system change its state? In quantum mechanics, one of the most important concepts is superposition. Superposition refers to a state where particles, like electrons or photons, exist in multiple places or states at the same time. This might sound impossible, but it has been shown repeatedly in experiments. For example, an electron in a superposition can be thought of as being in several different locations at once, or having several different spins simultaneously until it's measured. Once it is observed, It collapses into just one position or state, no longer existing in multiple possibilities. To help understand this, let's go back to the double slit experiment we discussed earlier. When particles are not observed, they seem to pass through both slits at once and interfere with themselves, acting like a wave. This is a type of superposition, where the particle is in a state of going through both slits at once. Only when we measure the particle to see which slit it passed through does it decide on one specific path. Quantum superposition is strange because it doesn't fit with how we experience the world. In our daily lives, we see objects in one place at a time, not spread out across multiple places. But at the quantum level, particles don't follow this rule. Superposition challenges our sense of reality, suggesting that at a small scale, things can exist in more than one state at the same time, only collapsing into a single reality when observed. Since superposition allows particles to exist in multiple states at once, some scientists have wondered if consciousness itself might be in a similar state. Could our minds somehow hold multiple thoughts, ideas, or even states of awareness at the same time? This might seem far-fetched, but some researchers believe that the human mind could work on principles similar to quantum mechanics, where our thoughts or perceptions could be superposed and not fully decided until we focus on them. Imagine making a decision. At some point, you may feel like you have multiple choices that are equally possible. It's as if your mind is in a superposition where you haven't yet settled on one option. When you finally decide, it feels like your mind collapses into that choice, leaving behind the other options. Some researchers think that consciousness might involve a similar process, where different mental states exist together until a focus or choice brings one of them into reality. This theory is still very hypothetical, but it raises interesting questions about how our mind might work. Could our thoughts or mental states actually overlap, only settling into clear thoughts when we focus on them? If this is true, it might mean that consciousness operates on a level similar to superposition, where possibilities exist until awareness selects one. Quantum superposition could also offer insight into certain mental states, such as creativity, intuition, or even decision-making. Sometimes, when people are being creative, they report feeling like their mind is open to multiple ideas or possibilities. It's almost like they're not bound to one way of thinking, but are open to many possibilities at once. This experience could be compared to quantum superposition, where all options or ideas exist together, and the mind hasn't yet chosen a specific one. Consider a situation where you're solving a problem. You might have several potential solutions in your mind at once, almost like different pathways. It's only when you focus on one of these ideas that you settle on a single solution. This way of thinking aligns with superposition, where the mind is open to multiple states or options until one is chosen. Quantum superposition could be a helpful analogy for these kinds of mental experiences, showing how we can hold various ideas or solutions in mind before deciding on one. Some scientists suggest that superposition could play a role in processes like intuition or gut feelings. Intuition is often described as an automatic sense of knowing without conscious reasoning. When people rely on intuition, it might feel like they're pulling from many possible thoughts or experiences at once, rather than logically working through them. In this sense, intuition could be like a mental superposition, where multiple ideas or bits of knowledge are present together, forming a gut feeling without a clear step-by-step process. Another area where superposition might be relevant to consciousness is memory and awareness. Memory allows us to hold past experiences in mind, but these memories are not always active. They remain in a background state until something triggers them. This holding of different memories or pieces of information could be likened to superposition, where different memories exist together, available but not fully active until needed. Imagine trying to recall a specific memory, like the name of a song you heard years ago. It might feel as if the memory is almost there, with different parts of it coming into awareness until you finally remember the name. In this way, the mind might be in a superposition of different possible memories, with one eventually coming to the surface. This idea doesn't mean that our memories are quantum states, but the concept of superposition could help us understand how different memories are present in the mind and become active when recalled. Some scientists believe that superposition might help explain states of awareness too. For instance, when we wake up from a dream, there's often a brief moment when reality and the dream world overlap in our minds. This in-between state could be similar to superposition, where both realities exist together, fading only as we fully wake up. Again, this is not to say that awareness is a quantum state, but the analogy of superposition could help explain these complex mental experiences. The idea that consciousness could work through principles like superposition is intriguing, but it's also highly controversial. Many scientists argue that superposition is a strictly quantum phenomenon that has no application to the brain or consciousness. Quantum effects, they say, are so small and delicate that they are unlikely to survive in the warm, wet, and noisy environment of the brain. Superposition and other quantum phenomena usually require highly controlled conditions, like those in a laboratory. Another criticism is that there is no clear evidence linking quantum superposition to brain activity or mental states. Neuroscience has made significant progress in understanding how neurons communicate, how memories are stored, and how different areas of the brain contribute to perception and awareness. So far, none of these findings suggest that quantum superposition plays a part. Critics argue that we should focus on what we know from neuroscience rather than speculative quantum theories when studying consciousness. Additionally, some scientists believe that concepts like superposition are simply being used as metaphors for consciousness. They argue that while superposition is useful in explaining quantum systems, it doesn't necessarily mean that the mind works the same way. In their view, comparing consciousness to superposition may be an interesting idea, but it doesn't provide any scientific explanation for how the brain functions. Despite these criticisms, the idea of superposition and consciousness continues to be explored. Some researchers believe that even if the brain doesn't function like a quantum system, the concept of superposition can still provide new ways to think about the mind. They see it as a tool for exploring mental states that don't fit easily into classical ideas of one state at a time. While we may never find direct evidence of quantum superposition in consciousness, these ideas encourage us to consider new ways of understanding the mind. Have you ever wondered if two things could be so connected that no matter how far apart they are, what happens to one immediately affects the other? In the quantum world, this isn't just a wild idea, it's reality. This strange connection is called quantum entanglement. But how does it work, and why is it so puzzling? Let's start with what quantum entanglement means. When two or more particles become entangled, their properties are linked, even if they're separated by vast distances. This means that measuring the state of one particle instantly changes the state of the other, no matter how far apart they are. It sounds almost magical, but it's one of the fundamental aspects of quantum mechanics. Imagine you have two entangled particles, A and B. You take particle A to one side of the universe and particle B to the other side. If you measure the state of particle A, you'll know the state of particle B immediately. It doesn't matter if they are light years apart. This instantaneous change defies our understanding of how information should travel. According to classical physics, nothing can travel faster than the speed of light. Yet, entanglement seems to break this rule. How can two particles communicate instantly, defying the cosmic speed limit? Albert Einstein famously called this spooky action at a distance. He struggled with the idea because it seemed to violate the principle that no information can travel faster than light. Einstein believed there must be hidden variables or unknown factors explaining how entanglement worked without breaking the rules of relativity. But experiments later showed that entanglement is real and can't be explained away by hidden variables. The particles really are connected in a way we don't fully understand. How did scientists prove this? This brings us to Bell's theorem, a groundbreaking discovery by physicist John Bell. Bell developed a series of experiments to test whether hidden variables could explain entanglement. The results showed that no classical explanation could account for the behavior of entangled particles. These experiments proved that quantum mechanics doesn't just describe our world in terms of probabilities, but also implies a deep and unavoidable connection between particles, no matter the distance. Bell's work left no room for classical hidden variable theories. Instead, it confirmed the non-local nature of quantum mechanics. This raises some big questions. Does the universe have a built-in connectedness that we don't understand? Is reality itself more unified than we think? Quantum entanglement challenges our ideas of separation and distance. If two particles remain linked over unimaginable distances, what does that mean for our understanding of space and time? It's a mystery that physicists still grapple with today. But entanglement isn't just a bizarre curiosity. It has practical applications. Quantum cryptography uses the principles of entanglement to create ultra-secure communication channels. In quantum cryptography, any attempt to eavesdrop on the communication disturbs the entangled state, revealing the presence of an intruder. This makes quantum cryptography incredibly secure, which is why it's being developed for future communication networks. Another application is in quantum teleportation. No, it doesn't mean teleporting objects like in science fiction. Instead, it refers to transmitting the state of a quantum particle from one location to another using entanglement. Scientists have successfully teleported quantum states over significant distances, which could lead to breakthroughs in communication and information transfer. One of the most ambitious ideas being explored is quantum computing. Quantum computers use entangled particles to perform calculations at speeds that are impossible for classical computers. Entanglement allows quantum computers to process vast amounts of data simultaneously, thanks to the phenomenon of superposition and linked quantum states. Though quantum computers are still in their early stages, they have the potential to revolutionize fields like medicine, artificial intelligence, and cryptography. If entanglement is so strange, why doesn't it affect our everyday lives? The answer lies in a concept called decoherence. Quantum effects like entanglement are delicate and easily disrupted. In the everyday world, particles constantly interact with their surroundings, causing quantum superpositions and entangled states to break down. This is why we don't see quantum entanglement influencing our macroscopic reality. It's a phenomenon that primarily exists in the isolated and carefully controlled environments of quantum experiments. Entanglement also raises questions about the nature of causality. In classical physics, if you change something here, it affects something over there in a predictable way. Cause and effect make sense. But with entanglement, there is no clear cause and effect in the usual sense. The connection between particles isn't one of sending a signal from one to the other. It's an instantaneous change that happens to both. This challenges our understanding of how the universe works and whether space and time are as straightforward as we think. Another big question is, does entanglement imply that everything in the universe is connected in some hidden way? If two particles can remain linked over vast distances, could there be a web of connections throughout the cosmos? This idea has intrigued physicists and philosophers alike, though we don't yet have the answers. Quantum entanglement is also being studied for its potential impact on quantum networks. These networks would use entangled particles to create secure, fast communication systems. Such networks could transform how data is shared, making it impossible for hackers to intercept information without detection. Still, for all the strange and promising possibilities, entanglement remains a mystery. It's one of those quantum phenomena that force us to rethink our basic assumptions about the universe. Is space as empty and separate as we imagine, or is it filled with invisible connections? If entanglement is real and fundamental, could it point to a deeper level of reality we haven't yet discovered? While some interpretations of quantum mechanics suggest that entanglement could hint at a hidden order or even a new way of understanding reality, we haven't reached a consensus. What we do know is that quantum entanglement challenges the classical worldview, opening up questions that we are only beginning to explore. Consider this: if particles are connected in ways we don't fully grasp, what implications might this have for the future of science? Could understanding entanglement unlock new technologies or even new physics? Or does it show us that the universe is far more complex and interconnected than our current theories can explain? It's a question that keeps physicists and thinkers endlessly fascinated. Entanglement is more than a quantum puzzle. It's a window into the mysteries of our universe, revealing just how little we still understand about the fundamental nature of reality. Have you ever wondered if empty space is truly empty? On the surface, it seems like a simple idea. When we think of a vacuum, we imagine a space with absolutely nothing in it. But in the quantum world, even emptiness isn't so simple. This is where the concept of virtual particles comes in. What are virtual particles, and why are they important? To understand this, imagine the universe as a restless sea. Even in a seemingly calm area, there are tiny, rapid ripples. Similarly, even the vacuum of space, when viewed through the lens of quantum physics, is full of activity. Virtual particles are short-lived pairs that pop in and out of existence. They aren't real in the way we usually understand matter, but they have real effects. How do virtual particles appear and disappear? They emerge from the quantum vacuum, which is the lowest possible energy state of a field. Because of the uncertainty principle, which limits how precisely we can know certain properties, these particles can briefly exist without violating any laws of physics. They form and annihilate each other almost immediately, leaving behind subtle but significant traces. You can't detect them directly, but they influence how particles and forces interact. One of the strangest phenomena involving virtual particles is the Casimir effect. Here's how it works. If you place two metal plates extremely close together in a vacuum, they experience a force pushing them toward each other. Why does this happen? The plates limit the types of virtual particles that can exist between them compared to outside, creating a pressure difference. The result is a measurable force, evidence that the quantum vacuum is far from empty. Why does the idea of the quantum vacuum matter? It suggests that the universe has an underlying, restless energy. This energy, called zero-point energy, exists even in the emptiest of spaces. Though zero-point energy is incredibly small, some theories speculate about its potential. Could it be harnessed one day? Could it even explain the mysterious forces, like dark energy, driving the expansion of the universe? We don't have concrete answers, but the quantum vacuum has sparked exciting possibilities. When scientists discuss quantum reality, the focus often shifts to whether our universe is fundamentally built on illusions or deeper quantum principles. For instance, some physicists think of reality as an emergent property of quantum fields. In other words, what we perceive as matter and solid objects may just be complex interactions of underlying fields and particles. But what does this mean for our understanding of reality? Take the concept of vacuum fluctuations. These fluctuations are momentary changes in energy that create virtual particles, highlighting that the vacuum isn't stable. But they also imply that space isn't as straightforward as it seems. Imagine our universe as a fabric constantly shifting at the smallest scales. Is what we perceive as solid and unchanging simply a product of all these tiny fluctuations? Virtual particles also play a critical role in particle physics. Consider force-carrying particles like photons, which mediate the electromagnetic force. Even gravity, the force pulling us down to Earth, could be influenced by these quantum fluctuations. Although we don't yet have a complete quantum theory of gravity, some ideas suggest that virtual particles in the quantum vacuum may interact with the gravitational field. Then there's the idea that virtual particles might contribute to the properties of elementary particles. For example, the mass of a proton isn't just from the quarks inside it. A large part of its mass comes from the energy of virtual particles that continually pop in and out of existence around the quarks. In this way, quantum fluctuations can shape the basic building blocks of matter. Another fascinating aspect of quantum reality is how it defies our sense of what is real or stable. Can we trust our senses if everything we perceive might be influenced by phenomena like virtual particles and fluctuating fields? Some physicists think our classical idea of a vacuum is an illusion created by these underlying activities. But how do we reconcile this with the everyday world, where things feel solid and definite? The concept of virtual particles also has profound implications for cosmology. The universe itself is thought to have emerged from quantum fluctuations in the early moments after the Big Bang. These fluctuations, though tiny, grew as the universe expanded, eventually leading to the formation of galaxies, stars, and planets. Without them, the universe might have remained a smooth, uniform sea of energy. Could it be that virtual particles hold the key to understanding why the universe is structured the way it is today? Furthermore, the existence of virtual particles raises the question, is the universe full of energy we haven't yet discovered how to access? If there is untapped energy hidden in the quantum vacuum, it could transform our understanding of physics. Some theories even suggest that this zero-point energy could be responsible for the mysterious dark energy that accelerates the universe's expansion. But how we could ever harness this energy remains a mystery. How do virtual particles fit into quantum field theory? This framework describes all particles and forces as fields that exist throughout space. Even a seemingly empty area contains these fields. Virtual particles are a manifestation of these fields, highlighting that no space is ever truly empty. Quantum field theory has been incredibly successful in explaining particle interactions and predicting the outcomes of experiments, but it still leaves some questions unanswered. Virtual particles also hint at the limitations of our current theories. For example, they contribute to the energy density of empty space, leading to a puzzle known as the cosmological constant problem. The amount of zero-point energy predicted by quantum field theory is vastly higher than what we observe. How can we resolve this huge difference? It's a puzzle that has baffled physicists and remains one of the great unsolved mysteries of physics. Have you ever thought about the implications of living in a universe governed by such strange quantum rules? If quantum fields and virtual particles form the foundation of reality, it challenges our understanding of what is real. Are we just observers in a quantum sea, perceiving patterns that arise from deeper fluctuations? Yet, despite the many unknowns, the concept of virtual particles provides a crucial link between quantum physics and cosmology. It gives us a glimpse of how the smallest quantum effects can influence the largest structures in the universe. It shows that even empty space is more complex than we imagined, full of invisible activity that might shape everything we see. So, as you think about the universe and everything in it, remember this: the seemingly solid world around us is shaped by forces and particles that defy intuition. Even the most empty places are buzzing with quantum activity, suggesting that reality is richer and more mysterious than we ever thought. Have you ever thought about how walls are meant to keep things out? It feels like a simple truth. If there's a barrier, it should stop anything from passing through. Yet, in the world of quantum mechanics, this isn't always the case. This is where the strange phenomenon of quantum tunneling comes into play. Imagine you're rolling a ball up a hill. If the ball doesn't have enough energy, it will roll back down without ever making it to the other side. That's how barriers work in our everyday world. But what if the ball, with no apparent reason, somehow appeared on the other side of the hill? This sounds impossible, right? Yet, at the quantum level, particles do something very similar. They can pass through barriers that they seemingly shouldn't be able to cross. How does this happen? Quantum tunneling is a result of the wave-like nature of particles. When we think about a particle like an electron, we usually picture it as a tiny solid object. However, in quantum mechanics, an electron can also be described by a wave function. This wave function represents all the possible places the electron could be. When this wave function reaches a barrier, a part of it can continue to exist on the other side. This means there's a small probability that the electron will tunnel through the barrier instead of bouncing back. You might wonder, why doesn't this happen in our everyday experience? The reason is that quantum tunneling is much more noticeable on extremely small scales, like with electrons or protons. Larger objects, like tennis balls or humans, have almost no chance of tunneling because their wave functions don't behave the same way. So, while tunneling is a common event for tiny particles, it's practically non-existent for the things we see and use daily. Quantum tunneling isn't just a bizarre theory, it has real-world applications. One of the most famous examples is in the Scanning Tunneling Microscope, STM. This device uses tunneling to produce incredibly detailed images of surfaces at the atomic level. Here's how it works. A very fine tip is brought extremely close to a material. Electrons tunnel between the tip and the surface, creating a current that depends on the distance between them. By moving the tip across the surface and measuring the current, scientists can map the surface with astonishing precision. But tunneling isn't just useful in microscopes. It also plays a crucial role in nuclear fusion, the process that powers the sun. In the sun's core, temperatures and pressures are unimaginably high. Yet, even under these extreme conditions, protons don't have enough energy to overcome the strong repulsive forces between them. Instead, quantum tunneling allows these protons to get close enough for fusion to occur, releasing the energy that lights and warms our world. Without tunneling, nuclear fusion wouldn't be possible, and the sun wouldn't shine. Another area where tunneling is significant is radioactive decay. Some unstable atoms emit particles spontaneously, and tunneling is part of this process. In the nucleus of an atom, particles are confined by a potential energy barrier. Quantum tunneling allows some of these particles to escape, leading to the atom's decay. This decay process helps us understand how certain elements change over time and is important in fields like geology and archaeology. Does quantum tunneling mean that all barriers are meaningless at the quantum level? Not exactly. The probability of tunneling depends on the thickness and height of the barrier, as well as the energy of the particle. Thicker or higher barriers make tunneling less likely. Still, even the tiniest probability can lead to significant effects when dealing with vast numbers of particles, as happens in stars and certain technologies. What's even more fascinating is how tunneling challenges the classical notion of impenetrable barriers. In classical physics, a barrier is either penetrable or not, depending on the energy of the object. Quantum mechanics, however, introduces a world where possibilities aren't so rigid. Instead, they're dictated by probabilities, and even the most solid walls might not be as impenetrable as they seem. Tunneling also forces us to think differently about energy conservation. How can a particle borrow energy to get past a barrier and still respect the laws of physics? The explanation lies in the fact that quantum mechanics allows temporary violations of energy conservation as long as they occur over very short timescales. This is a consequence of the Heisenberg uncertainty principle, which tells us that we can't precisely know both the energy and time for a quantum event. So, a particle can briefly borrow energy to tunnel through, as long as it gives it back right away. Can you imagine a world without quantum tunneling? Many of our modern technologies would be impossible. Consider the development of semiconductors, the materials used in computer chips. Tunneling affects how electrons move in these materials, making it essential for the operation of transistors, which are the building blocks of all modern electronics. Without quantum tunneling, we wouldn't have the computers, smartphones, or countless other devices that are now part of everyday life. Yet, the implications of tunneling go beyond technology. It raises questions about the very nature of reality. If particles can pass through barriers based on probabilities, does this mean reality isn't as fixed as we think? What if our understanding of boundaries, both physical and conceptual, is limited by the quantum rules that govern everything at its most fundamental level? Some scientists even speculate about how tunneling could be related to the origins of the universe. Quantum tunneling may have played a role in the early universe's inflation, a period of rapid expansion. Though this idea is still theoretical, it shows just how deeply tunneling is woven into the fabric of our understanding of reality. As strange as quantum tunneling sounds, it's a reminder of how different the quantum world is from our everyday experience. We live in a world that seems predictable and solid, but beneath the surface, there's a realm where probabilities rule, and particles can do things that defy our intuition. Does this mean the universe itself is full of surprises we're just beginning to understand? It certainly seems that way. Quantum tunneling also highlights the need for a deeper understanding of the connection between the quantum and classical worlds. How do these two realms coexist? Why do quantum effects like tunneling become negligible on larger scales? These are questions that continue to puzzle and fascinate physicists, pushing them to search for new theories that can explain the quantum world's mysteries. So the next time you think of a wall or a barrier, remember that in the quantum world, nothing is quite as definite as it seems. Even the most solid structures may have quantum secrets waiting to be discovered. How certain are we about what we know in our daily life? If we measure a cup's volume or a car's speed, we expect precise numbers. But in quantum mechanics, certainty is not so simple. Have you ever wondered if we could know everything about a particle state with absolute precision? The Heisenberg uncertainty principle tells us otherwise. So, what exactly is this principle? It states that we can't know both the exact position and the exact momentum, which depends on speed and mass, of a particle at the same time. If we try to pinpoint a particle's position with extreme accuracy, our knowledge of its momentum becomes uncertain, and vice versa. The principle isn't just a limitation of our measuring tools, it's a fundamental feature of the quantum world. Imagine you're trying to measure a tiny particle, like an electron. If you want to see exactly where it is, you have to use light or some kind of wave to observe it. But the smaller the particle, the higher energy you need for this wave. When you hit the electron with a high-energy photon, it changes the electron's momentum. It's like trying to take a close-up photo of something delicate, but the act of taking the photo ends up disturbing the object. So, even before we attempt to measure, the very act of observing introduces uncertainty. But why can't we escape this limitation? To answer this, think of the wave-like nature of particles. An electron isn't just a point in space. It's described by a wave function, a mathematical description that gives the probabilities of where the electron might be found. If the wave is very spread out, the particle's position is uncertain, but its momentum is more definite. If the wave is tight and localized, the particle's position is clear, but the momentum becomes uncertain. The more we narrow down one of these aspects, the more the other blurs. How does this uncertainty affect our understanding of the universe? It challenges the classical idea that everything follows precise, predictable paths. In the everyday world, we assume that if we know where something is and how fast it's moving, we can predict where it will be in the future. But in the quantum world, this kind of precise prediction is impossible. Instead of certainty, we deal with probabilities. This change from a deterministic to a probabilistic view is profound. For instance, when we talk about an electron in an atom, we can't say for sure where it is. We only know the probability of finding it in a certain region. The uncertainty principle plays a crucial role in the structure of atoms. If electrons could have both a well-defined position and momentum, they would spiral into the nucleus, and atoms as we know them wouldn't exist. Instead, the uncertainty principle keeps electrons spread out and stable, forming the atoms that make up everything around us. You might ask, does this uncertainty apply only to the microscopic world? It does, but it's so small that we don't notice it on larger scales. For example, when we talk about a car or a ball, the uncertainties in position and momentum are so tiny that they're irrelevant. The classical world seems predictable because the quantum uncertainties average out. Now, let's dive into the probabilistic nature of quantum mechanics. Unlike classical physics, which deals with definite outcomes, quantum mechanics describes reality in terms of probabilities. Instead of asking where a particle is, we ask where it is likely to be. When we make a measurement, we don't find the particle in several places at once, even though its wave function spread across different locations. We find it in a specific spot, and the wave function collapses to reflect that. This brings up a big question. Why does the wave function collapse when we measure it? The short answer is that no one knows for sure. This idea of collapse is one of the most mysterious parts of quantum mechanics. Before measurement, the particle exists in a superposition of all possible states. But the moment we observe it, the wave function suddenly decides on a specific outcome. Does the act of measurement cause reality to become definite? Or is it something else entirely? Another way to think about quantum uncertainty is by looking at the position and momentum of particles. If you could know an electron's exact speed, you wouldn't have a clue where it is. If you tried to pin down its exact location, you'd lose all information about how fast it was moving or in what direction. These are not just measurement problems. They reflect the limits of what nature allows us to know. To illustrate how quantum uncertainty can seem strange, consider an experiment where we shoot electrons through a narrow slit. As we make the slit narrower to get a better idea of the electron's position, the uncertainty in its momentum grows. This increased momentum uncertainty causes the electron to spread out and travel in unpredictable directions. In other words, trying to make one thing certain creates more uncertainty elsewhere. What does this probabilistic nature mean for the world we live in? It suggests that, at its core, reality might not be as fixed as we think. Classical physics assumes that everything has a definite state at any given time, even if we don't know it. Quantum mechanics challenges this view, proposing that particles don't have definite states until they're measured. Until then, they exist in a blend of possibilities. If quantum mechanics is all about probabilities, how does it impact things like energy levels in atoms? It turns out that energy levels are also subject to uncertainty. Electrons and atoms have quantized energy levels, meaning they can only exist in specific energy states. But even within those states, there is a small uncertainty in energy. This energy uncertainty becomes significant in quantum phenomena like virtual particles popping in and out of existence, an idea connected to the uncertainty principle. Does the uncertainty principle mean that everything is unpredictable? Not quite. While individual particles behave unpredictably, the behavior of large groups of particles becomes predictable. That's why classical physics works so well for everyday objects. The uncertainties of countless particles average out, giving us a world that appears certain and follows clear rules. Quantum uncertainty also plays a role in advanced technologies. For instance, it affects how transistors work in computers. Transistors control the flow of electrons, and quantum effects like tunneling, which we discussed earlier, depend on these principles of uncertainty. Understanding quantum mechanics is crucial for designing smaller and more efficient electronic devices. The Heisenberg uncertainty principle and the probabilistic nature of quantum mechanics also lead to philosophical questions. If we can't know everything about a particle's state, does that mean the universe is inherently unpredictable? Or are there hidden variables we haven't discovered yet? Some physicists have proposed theories that introduce hidden variables, but so far, these ideas haven't provided a clearer picture of quantum uncertainty. As we keep exploring these concepts, one thing is clear: quantum mechanics shows us a world full of possibilities. The certainty we're used to in the classical world doesn't apply to particles at the quantum level. Instead, we're left with a reality governed by chance and probabilities. The mysteries of quantum mechanics continue to challenge our understanding, pushing us to think beyond what seems obvious. Does this mean we'll ever fully understand the universe's fundamental nature? It's hard to say, but the journey of discovery is what makes science so exciting. And as we learn more, the line between what we know and what we can never know keeps shifting, revealing a world more complex than we ever imagined. Let's start with a question. How does reality work if particles behave unpredictably at the quantum level? Quantum mechanics offers several theories to explain how particles interact and behave. each trying to address the strangeness of the quantum world. One of the most discussed is the Copenhagen interpretation. What does the Copenhagen interpretation say? This approach, introduced by Niels Bohr and Werner Heisenberg, suggests that quantum particles don't have definite properties until they're observed or measured. Until we observe them, these particles exist in a state of probabilities. When a measurement is made, the wave function describing all possible states collapses into one actual outcome. This view is strange, right? Imagine you're looking at a ball. In the classical world, the ball has a definite position and speed whether you're observing it or not. But in the quantum world, a particle like an electron only decides on a position or speed when you measure it. Before that, it's like a mixture of all possibilities. So, is reality dependent on observation? Does something only become real when we look at it? Let's think about Schrodinger's famous thought experiment, Schrödinger cat. In this experiment, a cat is placed inside a box with a quantum device that has a 50-50 chance of killing the cat based on the behavior of a subatomic particle. According to the Copenhagen interpretation, until we open the box and observe the situation, the cat is both alive and dead. Only when we look inside does the wave function collapse, and the cat's fate becomes real. It's as if nature waits for our observation before deciding what's true. Isn't that bizarre? It makes us question the nature of reality itself. But not everyone is satisfied with this explanation. In fact, the Copenhagen interpretation has sparked endless debates. How can something not be real until it's observed? This leads us to our next question. Are there other theories that make more sense? One such alternative is the many worlds interpretation, proposed by physicist Hugh Everett. Instead of particles choosing one outcome when observed, this theory suggests that every possible outcome of a quantum event actually happens. When you measure something, the universe splits into parallel versions of itself, each reflecting a different outcome. In one universe, Schrödinger cat lives. In another, it doesn't. So, do we live in a multiverse of branching possibilities? The many worlds interpretation suggests that every time a quantum choice is made, a new reality forms. Think about the consequences of this. Every decision, every random event creates a new universe. It sounds like science fiction, but some physicists take it seriously. Yet, there's a big problem. If all these worlds exist, why can't we detect them or move between them? The idea of parallel universes is mind-boggling. However, the many worlds interpretation does solve one problem. It gets rid of the idea of wave function collapse. Instead, the wave function continues, and all possibilities become real somewhere. But if that's true, does it mean there are infinite versions of you, each living a different life? The theory raises as many questions as it answers. What about theories that bring back a sense of certainty, like the pilot wave theory? This theory, first proposed by Louis de Broglie and later developed by David Bohm, reintroduces a kind of determinism to quantum mechanics. According to the pilot wave theory, particles are guided by an invisible wave called a pilot wave. This wave determines the path of the particle, making everything predictable if we knew all the details. Unlike the Copenhagen interpretation, the pilot wave theory suggests that particles always have definite properties, even when they aren't being observed. The wave function isn't about probabilities, but is an actual wave influencing the particle's motion. Does this make quantum mechanics less mysterious? In some ways, yes, but it still doesn't explain everything. For example, the theory still has to account for the wave-like behavior of particles and match experimental results. If particles always have definite states, why don't we notice this in our measurements? One reason is that the pilot wave remains hidden, making it hard to distinguish this theory from others. Pilot wave theory challenges the mainstream views, but doesn't have enough experimental evidence to fully replace them. Still, it keeps the debate about quantum mechanics alive, offering an alternative view of reality. With so many competing interpretations, how do we decide which one is right? The truth is, we don't have all the answers yet. Quantum mechanics works incredibly well for calculations and predictions, but it leaves us with a deep puzzle of the nature of reality. Some physicists believe we need a completely new theory to make sense of it all. Others think we should just accept the weirdness. Let's discuss one more question. How do these interpretations impact our understanding of the universe? If reality depends on observation, does that mean the universe needs an observer to exist? Or if there are infinite parallel worlds, what does that say about free will and our choices? And if a hidden wave guides everything, does that mean the universe is ultimately deterministic? These theories show that our classical view of a predictable, concrete world doesn't apply at the quantum level. The Copenhagen interpretation emphasizes the role of the observer, suggesting that reality isn't set until we observe it. The many worlds interpretation takes a more radical approach, proposing that every possibility plays out in a separate universe. The pilot wave theory, on the other hand, seeks to restore order and predictability to quantum mechanics. Each theory has its supporters and critics. The Copenhagen interpretation is the most widely taught and accepted, but it leaves many feeling unsatisfied. The many worlds interpretation is fascinating but untestable. The pilot wave theory appeals to those who crave a deterministic universe, but it's hard to prove. Where does this leave us? Quantum mechanics continues to be a field full of debates and new ideas. No interpretation has all the answers, and new theories may emerge as we learn more. Until then, the quantum world remains one of the greatest mysteries of science. Let's dive straight in with a simple question. How does quantum mechanics impact our daily lives? You might think quantum theories are too abstract to matter outside of physics labs, but they actually shape some of the technology we use and the way we think about reality. First, consider quantum computing. What makes a quantum computer different from a classical one? In a regular computer, information is stored in bits that are either a 0 or a 1. Quantum computers use qubits, which can be 0, 1, or both at the same time because of quantum superposition. This ability to exist in multiple states allows quantum computers to process vast amounts of information simultaneously. It's like being able to read every possible outcome of a book at once instead of flipping through each page. How does this affect our understanding of computing? Classical computers work through problems step by step, but a quantum computer can explore many paths simultaneously. For example, if you wanted to break a complex code, a quantum computer could test all possible solutions at once. This makes quantum computers incredibly powerful for tasks like cryptography, simulating molecules for drug discovery, and optimizing complex systems. Yet, this doesn't mean quantum computers will replace our laptops. They're useful for specific problems that require immense processing power. Building a fully functional quantum computer remains a challenge because qubits are very sensitive to their environment. Even tiny disturbances can cause errors, a problem known as quantum decoherence. This issue still puzzles researchers who are trying to make these computers more stable. Another area where quantum mechanics has a big impact is quantum cryptography. How can we make communication perfectly secure? Quantum cryptography uses the principles of quantum mechanics to create unbreakable encryption. One popular method is called quantum key distribution. It relies on the idea that observing a quantum system changes it. If an eavesdropper tries to intercept a message encrypted with QKD, the act of measuring the quantum data will alter it and alert the sender and receiver. Why does this matter? In an age of increasing cybersecurity threats, quantum cryptography offers a way to secure sensitive information. Governments and corporations are investing heavily in quantum communication to protect data. But like quantum computing, quantum cryptography isn't without its challenges. Practical implementation on a large scale is still difficult, and there are limits to the distances over which quantum keys can be distributed. What about quantum sensors? Quantum mechanics is also used to make extremely precise sensors for things like measuring gravitational waves or imaging the human brain. These sensors exploit quantum properties like entanglement and superposition to detect minute changes in the environment. For instance, atomic clocks, which use the quantum oscillations of atoms to keep time, are so accurate that they only lose 1 second every billion years. How do these sensors affect our lives? They enable more accurate GPS systems, better medical imaging techniques, and sensitive detection equipment for scientific research. Quantum sensors could also play a role in navigation systems that don't rely on satellites, which would be useful in places where GPS signals are blocked. Next, let's discuss the strange field of quantum biology. Can quantum mechanics explain some processes in living organisms? This area of research is still developing, but there are intriguing possibilities. For example, photosynthesis in plants is thought to use quantum effects to transfer energy efficiently. The energy from sunlight is converted into chemical energy with almost no loss, and quantum coherence might help guide this process. Another example is bird navigation. How do birds like robins migrate over long distances with precision? One theory is that birds use quantum entanglement in their eyes to detect the Earth's magnetic field. Special proteins called cryptochromes might enable this sense. The idea is that when a bird's eye absorbs light, a pair of entangled electrons is created. The magnetic field influences these electrons, helping the bird navigate. Quantum mechanics might even play a role in how our sense of smell works. Some researchers suggest that our noses can detect specific molecules based on quantum vibrations rather than just the shape of the molecules. If proven, this would be another example of quantum effects in biological systems. The applications of quantum mechanics keep expanding. Technologies like quantum imaging allow scientists to see things that were previously invisible. By taking advantage of quantum entanglement, researchers have developed cameras that can take detailed images of cells and tissues without damaging them. These advances could revolutionize medicine and lead to earlier, more accurate diagnoses. Why do these technologies work? It all comes down to the principles of quantum mechanics, where particles behave in unpredictable and non-intuitive ways. The fact that quantum effects can be harnessed in real-world applications shows that quantum theory isn't just theoretical, but has practical consequences. However, many of these technologies are still in the early stages, and there is much we don't yet understand. Does this mean quantum technology will soon be everywhere? Not quite. While quantum advancements are promising, they come with limitations. For example, quantum computers and sensors need highly controlled environments to function. Even tiny disturbances can throw off quantum states. Researchers are working on making these technologies more practical, but there's still a long way to go. Lastly, think about how quantum mechanics makes us rethink our everyday experiences. We live in a world where classical physics seems to explain most things, like the motion of cars or the way light behaves. But on the smallest scales, quantum mechanics tells a different story, one full of uncertainties and probabilities. Quantum mechanics challenges our ideas about determinism and certainty. We are used to a world where causes have clear effects, but in the quantum realm, things are often unpredictable. How do we reconcile these differences? This question remains one of the most intriguing aspects of quantum mechanics, and as technology evolves, it may help us understand more about the universe and ourselves. The impact of quantum mechanics on technology is already significant, and its potential continues to grow. From quantum computing and cryptography to quantum biology and sensors, the practical applications are just beginning to unfold. As these technologies develop, we'll likely find even more ways that the strange, non-intuitive world of quantum physics can be applied to improve our lives. But for now, we're still learning and exploring, trying to understand the mysterious quantum illusions that make it all possible. Imagine a mystery where the very nature of reality seems to be playing tricks on us. How can something behave both like a particle and a wave? This is the puzzle we encounter when we talk about wave-particle duality. It's a concept that goes against everyday experience, yet it's a cornerstone of quantum mechanics. Let's dive into one of the most famous experiments that expose this strangeness. Have you ever wondered if light is a wave or a particle? For a long time, scientists debated this question. Then, in the early 1800s, Thomas Young performed the double-slit experiment. Here's how it worked. Young shined a beam of light through two thin slits cut into a barrier. On the other side of the barrier, he placed a screen to observe what would happen. If light were made up of particles, you'd expect it to create two bright lines on the screen, one behind each slit. But if light were a wave, the waves would spread out, overlap, and create a pattern of bright and dark bands called interference. The result? Light produced the interference pattern, showing it behaved like a wave. But the story doesn't end there. As technology advanced, scientists conducted the experiment with particles, like electrons, instead of light. The expectation was that electrons, being particles, would behave differently. But when electrons were shot one by one through the slits, they still created an interference pattern over time. It was as if each electron passed through both slits simultaneously, like a wave, and then interfered with itself. How is that possible? When scientists tried to measure which slit the electron passed through, something even more bizarre happened. The interference pattern disappeared, and the electrons behaved like particles. It seemed that simply observing or measuring the electrons changed their behavior. So, what's going on? Is reality truly wave-like until we look at it? This experiment shattered the classical view of particles as little, solid balls with predictable paths. In quantum mechanics, particles like electrons are not just particles. They also have wave-like properties. The experiment showed that the very act of observing could change the outcome, challenging our intuitive understanding of how things should work. This brings us to the concept of particle and wave duality. Not only does light, composed of photons, exhibit this duality, but so do material particles like electrons and even larger entities under certain conditions. Light, at times, acts as discrete packets called photons. You can imagine photons as tiny bullets of energy, but at other times, light spreads out and interferes with itself as if it's made of continuous waves. This dual behavior isn't limited to light. Matter, like electrons, protons, or even whole atoms, also displays wave-like characteristics. So, are these things waves or particles? The answer is they are both, but not in a way that fits neatly into everyday logic. Let's pause and think about this for a moment. If particles like electrons can behave like waves, then what does that mean for the nature of reality itself? How can something be a particle and a wave simultaneously? The quantum world introduces the idea of superposition, a principle stating that particles exist in multiple states or positions at the same time. In the case of the double-slit experiment, the electron can be seen as existing in a superposition, going through both slits simultaneously. This idea leads to the concept of the wave function, which is a mathematical description of the quantum state of a particle. The wave function doesn't tell us exactly where a particle is, but rather the probabilities of finding it in different places. Picture it this way. If you imagine rolling a die, the die in classical terms lands on a specific number, let's say a 3 or a 5. But in the quantum world, the die would be in a superposition of all possible numbers until you look at it. Only when you observe the die would it settle on one number. That's the strangeness of superposition. The double-slit experiment seems to show that particles have a similar nature, existing in all possible states until they are observed. This raises a haunting question. Does the act of observation create reality? Or is there a deeper mechanism at work? Interference plays a key role in this mystery. The wavy patterns we see are a result of interference, where waves overlap and either amplify or cancel each other. In quantum mechanics, the wave function of a particle can interfere with itself, creating patterns that seem to reflect the particle's choices. What's even more perplexing is the role of the observer. When scientists placed detectors to see which slit the electron passed through, the interference pattern disappeared. The electrons no longer behaved like waves, but like particles, making distinct marks on the screen. It's as if the electrons knew they were being watched and decided to behave differently. This phenomenon is called the observer effect, and it turns our understanding of reality upside down. So, we're left with a paradoxical world where the simple act of observing can change how things behave. How can electrons or photons display both wave and particle characteristics depending on whether we measure them? It's not just a matter of curiosity. This duality is essential for understanding everything from how light travels to how electrons move in atoms. It also forms the basis for modern technologies like quantum computing and electron microscopes. Wave-particle duality isn't just a weird quirk of quantum mechanics. It's a profound truth that challenges our understanding of reality. The double-slit experiment, with its seemingly simple setup, opened a doorway to a world where the rules we take for granted no longer apply. Are we observing particles that transform into waves, or waves that become particles? Or is there a third explanation waiting to be discovered? Quantum mechanics invites us to ponder these questions and accept that the universe is more mysterious than we ever imagined. We might imagine a complete void, an absolute nothingness. But according to quantum physics, even the emptiest parts of space are far from empty. They are full of activity, buzzing with something called zero-point energy. So, what exactly is zero-point energy? Even at absolute zero, the lowest temperature possible where all classical motion stops, quantum fields are still restless. Particles flicker in and out of existence, vibrating with energy. These aren't ordinary particles. They are known as virtual particles. They appear and disappear too quickly to be directly observed, but they still have real effects on the world around us. What kind of universe has energy stored even in the places that seem completely empty? Now, how does this quantum vacuum relate to consciousness? Let's venture into some fascinating, yet highly debated territory. There are theories that try to connect consciousness with quantum phenomena, and some thinkers even propose that consciousness might interact with the fabric of reality in ways we don't yet understand. One idea is that consciousness might be linked to these quantum fields that permeate the universe. Why do some people think this way? Quantum mechanics is famous for its observer effect. The act of observing a quantum system seems to change its behavior. In some interpretations, this raises a perplexing question. Does consciousness play a role in shaping reality? If a particle state collapses when measured, does a conscious observer have a part in this collapse? The thought is intriguing, though most scientists are cautious. There's no hard proof that consciousness affects quantum systems. Still, certain interpretations, like the von Neumann-Wigner interpretation, suggest that consciousness could be fundamental in the quantum measurement process. According to this idea, consciousness isn't just a passive observer of the universe, but an active participant. Does that mean our minds are connected to the quantum field somehow? It's hard to say, but the idea keeps the conversation going. Let's bring back zero-point energy for a moment. If we imagine a universe filled with quantum fields and energy fluctuations, could consciousness interact with this complex structure? Some researchers argue that consciousness may arise from these fields or influence them. However, this hypothesis is speculative. There's no direct evidence linking the two, but it shows the hunger we have to understand the ultimate mysteries of our existence. Another theory that brings consciousness into the quantum picture is orchestrated objective reduction, ORCO-R, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. Consciousness could arise from quantum processes happening in the brain's microtubules, tiny structures found in neurons. Penrose and Hameroff argue that these microtubules could harness quantum coherence, meaning the brain might operate in ways that regular neuroscience doesn't yet explain. But many scientists remain skeptical because the brain is warm and messy, not an ideal environment for fragile quantum states. Let's ponder this. What if the brain and quantum fields are connected in ways that current science doesn't fully understand? If quantum mechanics shapes the fundamental nature of reality, could it also shape consciousness? The idea might sound wild, but it reflects the uncertainties we face in both physics and neuroscience. The mind itself, with all its thoughts, dreams, and perceptions, is one of the greatest puzzles. And here's another angle to consider. Some spiritual or metaphysical traditions claim that consciousness is more than the brain's activity and might have a deeper connection to the universe. While these views are not based on scientific evidence, they resonate with the notion that the universe holds mysteries we haven't unraveled. Even Einstein once wondered if there's a deeper order beneath the surface, some unifying principle that connects everything. Now, let's not get carried away. Mainstream science is cautious about linking consciousness to quantum physics. The brain is a complex system, and many neuroscientists believe that classical physics explains most of its functions. But the weirdness of quantum mechanics tempts us to question whether consciousness, that core of our experience, could be more extraordinary than we think. The quantum vacuum, filled with zero-point energy, is a place of constant fluctuation, a reminder that the universe's simplest building blocks are dynamic. In a way, it mirrors the restlessness of human consciousness, always active, always searching for meaning. We don't have definitive answers, but exploring these questions shows how deeply connected physics and philosophy can be. So, as we look out at a universe teeming with unseen energy and wonder about our own awareness, we find ourselves at the intersection of science and the unknown. The quantum world and our conscious experience both defy easy explanations. They make us ask, what does it mean to truly understand the world? And is there more to reality than what we can observe with our senses and measure with our tools? These are the questions that keep the debate alive and our curiosity engaged. As we journey through the strange and mysterious world of quantum mechanics, we uncover more questions than answers. The quantum vacuum, zero-point energy, and the potential link between consciousness and quantum fields invite us to reconsider what we know about reality. Are we merely observers, or do we play an active role in shaping the universe around us? While the answers remain elusive, the exploration itself opens doors to a deeper understanding of existence. In this endless dance of particles, energy, and consciousness, one thing is certain: the mystery of quantum mechanics will continue to captivate and challenge us. If you enjoyed diving into these mind-bending ideas, don't forget to give this video a thumbs up. And if you're ready for more deep dives into the wonders of the cosmos, hit that subscribe button and turn on notifications so you don't miss a thing. Thanks for watching, and I'll see you in the next video.